Okay, let's see if we can make some sense of this right-hand rule here. So I'm going to start off with this diagram, and I'm showing a magnetic field which is going straight down into the page. So we have little X's, the little crosses, so that means that the magnetic field is down into the page. And I'm going to show a positive charge which is moving to our left. So using our right-hand rule, we have our forefinger point in the direction of the magnetic field. That's straight down. The thumb represents the velocity of the positive charge, so that's to the left. I'm probably blocking it there. And that means that the force comes straight towards us, or straight down on the screen as you're looking at it here. So magnetic field is straight down, the thumb is in the direction of the motion of the charge, the velocity of the charge, and the force is 90 degrees to both of those, which means it comes toward us. So that means that the velocity on this particle as it moves through this magnetic field is downward, which means it will start to follow a curved path because there's a force acting on it toward me. Now notice that once the force is acted on it, it is now moving in a different direction, which means that the force changes direction, which changes the direction of the particle again, which changes the direction of the force, and so on. And what you'll wind up with is, if the area of the field is large enough, this charge will just follow a circular path. As long as it is perfectly perpendicular to the magnetic field lines, it will just follow like a circular. It's just kind of trapped in there. It just follows a circular path around and around. Also notice that the particle will not speed up or slow down because the force on the particle is always perpendicular to its motion. So the magnetic field is not contributing a force in the direction of its motion. So it will not speed up and it will not slow down. It will simply change direction. Kind of an interesting thing. Okay, here's another example. In this case, we have a magnetic field which is rising straight up out of the page. And let's say that we have a positive charge, and we're going to have it go in this direction, so I guess north on the page, and see what that does. So this is probably going to break my arm, but hey, it's for science. So the magnetic field is coming out of the page, so that is going to be straight up toward the camera lens here. The direction, the velocity of the charge is that away, and that means that the force is to our right. Okay, so the magnetic field is coming up. The velocity of the charged particle is upward on the page, and then the force is going to be 90 degrees to both of those, so the force on it is going to be in this direction. And again, it'll start to follow a curved path as we go. All right, let's see if we can do one more here. We're going to make the magnetic field lines go this way. So they're in the plane of the page and they're moving to our right. And let's send our charged particle, let's make it an electron this time, okay? It's an electron, and we're going to say that it is going this direction. Okay, so we're going to use the right-hand rule again. We will set the direction of the magnetic field in this direction. The direction of the electron is upward on the page, and the force is straight down, except that it's an electron. And the right-hand rule is for positive charges. So that means that instead of the force being down into the page, it'll be the opposite of that and will actually be coming straight up. Now, if you like to use a left hand for electrons, because it's the opposite charge, magnetic field goes that way. The force on, the velocity of the electron is that way, and the force on the electron comes straight up. So you can use whichever you choose. You can use the right hand, and remember that negative charges have opposite force, means the force coming upward. Or you can use the left hand rule, and everything will work out just fine. Okay, now here's an interesting example. It's on page 781 in your textbook, but it's not intuitively obvious what they're getting at here, so I'm going to talk about it a little bit. They're talking about how charged particles from the solar wind, when they encounter Earth's magnetic fields, why those charged particles tend to get funneled to the poles where they make the northern and southern lights, the aurora borealis and the aurora australis. So what happens is a charged particle comes in, say, from this direction, and it encounters the magnetic field lines from the Earth, which run from the South Pole to the North Pole, by the way. More on that later. Now, if the charged particle were to happen to hit exactly on the equator, right where the magnetic field lines are running exactly perpendicular to the direction of the solar wind, then we'd have that case where the charged particle is going to be trapped and just going to go around and around in a circle. And it's going to be trapped there kind of in a band around the equator. That's shown on this example here on B. It's the idea where the charged particle comes in. It's the charged particle is in the plane of the page, and the magnetic field is rising vertically straight out of the page, and so the charged particles get trapped in a circle. Now, it's slightly different if it's a little bit north of the equator or a little bit south of the equator, because now there's an angle between the path, the velocity of the charged particle and the magnetic field. And the result of that is that the particle does not speed up or slow down, but it does follow a spiral path along the, making a helix around the field line, which carries it to one pole or the other. If it encounters the Earth a little south of the equator, it gets funneled to the South Pole, and if it's north of the equator, it gets funneled to the North Pole, because it kind of rides along the field line itself. And then when the charged particles crash into the atmosphere, they ionize the atmosphere and turn it into a plasma slightly, and it glows with light, and there we have it. We have aurora borealis. Now, you may have heard of the Van Allen radiation belts. Maybe you have, maybe you haven't. That's not something you need to know for AP physics, but it turns out that along the equator of really all of the bodies in the solar system that have magnetic fields, except maybe the sun, but there are bands where there are charged particles that get trapped by the magnetic field, even with the equator. And if you send satellites through that, there's so many charged particles trapped there that can start messing with the electronics in the satellites. And this is the reason for it. It's charged particles which have encountered the magnetic field lines perpendicular to their path, and so they just kind of get trapped there. They go around and around and around, and they don't get funneled to either the North Pole or the South Pole. Now, that's not a forever thing, but they get stalled there kind of in purgatory for a little while until finally they slide out one side or the other, and then they crash into the atmosphere. But as a result of this, there's a higher concentration of radioactive particles even with the equator. All the way around. It's kind of a belt of radiation that goes around the equator of bodies like the Earth. It's most pronounced around Jupiter. They have to be pretty careful when they send space probes through there, make sure their electronics are hardened so they don't get messed up. Anyway, kind of an interesting application for it, and they do explain it pretty well on page 781.